takes a lot of force to move it. This is a plot of the amount of force required, the amount of force being applied across that spool, and there is a high amount of force over here, a low amount of force down here, and the flow rate. This is a fast flow, this is a slow flow, so it's the opposite way around to what you might expect. So this up here is closed, and what happens is we increase the force across this spool, goes this way, and it follows this line here. And when it reaches a certain amount of force, the valve spool will move, drop down, and as it moves, the flow rate will slow down significantly. And then what we do is we open up the valve again and we reduce the amount of pressure on it, and as the pressure reduces, it will suddenly open. So that's what that data shows. So this is sitting in the open position, waiting for for another signal to come in, and then suddenly we start applying more pressure, a little tiny bit of pressure. It causes a spike here. I don't know if you saw that spike. That bit there is sort of shoots up, overshoots where it was before, and comes back to the closed position. So you can see, if I pause this at the right time, no. You can see that there's a spike here and some hysteresis building up inside this valve. And that's a sign that the behaviour is getting worse and worse inside this valve. So this is, we try and say, okay, how can we detect the early signs of that stiction building up? And we do various types of analysis on that signal. This is one of the, I think this is the pressure signal here. I don't know if you can see, but there's a, this is the pressure signal going in. So this is a time series. We've got the frequency content in that signal, and we've got a time frequency analysis of the data. This is when the valve is opening. You get a lot of energy coming in the system. This is the valve in the open state, and this is when it closes. And we're looking at what symptoms are there in that data that tell us that something's happening. Okay. And what we do with that is we then take that information, we try and build a model of the valve starting to go wrong. And we've got this information, we build this model. We can do a lot with that then. Once we've got this model of stiction building up and how it occurs, we've then integrated that into system models of the whole fuel system inside a gas turbine engine, looked at the effect of those faults coming in, and starting to do analysis and develop various types of detection algorithms to see what the effects are and see whether we can detect these builds-up of lacquering within the system. So that's some work we've been doing on monitoring the degradation in a fuel system valve. Another source of data that we have is a small rig we've built down the bottom of the lab, which is representative of the components inside a gas turbine engine. So let's see what we can see. So there's a pump on here. The fluid flows out the pump through a flow metering unit into a control valve, and here you can see better. There's an actuator with some frictional load on it. There's the ability to measure the position of the actuator. The valve here, this is the position control valve, be able to monitor various parameters inside that valve. And we can do all that both for the normal condition and also for various fault conditions that we can inject into the system. So faults we might see might be some leakage in the actuator. The seals start to degrade, fluid starts flowing through the hydraulic ram when it shouldn't. We can simulate that sort of behaviour. Various frictional loads changing. We can add different frictions. the stiction inside that valve, we can combine what we've got with our models that we built from the previous bit of work. We've collected real data. We can combine that and simulate that on this rig setup and start applying the algorithms to a whole system. We can also look at various different types of component wear. So as a very crude example, this is the response of the rig. This is the actuator moving, the blue line, as we change the valve. We're opening and closing the valve here, and it's making the actuator move in and out. This is the normal behaviour you expect to see. A particular fault condition might do something like changing the dynamics of the actuator. We had some particular type of friction load, and we see very severe change in that, where the response is very much slugged, very much slower. You should be able to see the gradient of that line, the velocity of that line is much slower. The amount of time it stays at its set point is much shorter because of that. And that is quite an easy one to detect. You could do that with a very simple modelling technique. We've been looking at various approaches to that and trying to assess the benefit of those approaches. This graph is for two different fault diagnosis features. One of them, what we've called the advanced feature. This is looking at the very high frequency content in that signal. What can we tell at a kilohertz, 10 kilohertz, 50 kilohertz about the very small effects that are happening because of these faults that we put in? So we can compare these features with features that could be implemented today. We're using the current sample rates that are on an engine. And we look at what advantages are there of taking these advanced features. This graph shows the magnitude of the fault that's been injected and the response of the algorithm. So we want an algorithm that responds when there is very little fault that's being injected into the system. The traditional feature, you need to wait until about half of the fault magnitude enters the system. Whereas if we are to take different approaches to use the same sensor as it happens, but just sampled at a much higher rate, we can detect that fault much earlier. So there is an advantage. We show here there is an advantage of an enhanced, what we've called here, enhanced data usage. So increasing the amount of data that we use to build the algorithms when compared to the current system. And then we would follow up this work is to then say, okay, what if we had a different type of sensor? What if we had a strain sensor that was measuring the actuator position, or a accelerometer that was even more sensitive? And we could plot all these different approaches, look at the costs associated with each of those sensor types and the software needed to process them, and to work out which was the best. And we could then link that back into the benefits modelling that we had down here. So, okay, we can detect this fault, I don't know, 50% earlier than the other one. What advantages does that give us in terms of being able to stop your aircraft sitting on the runway while you're waiting for it, to stop the delays and isolations and the costs associated with that? Do we finish it 3 or 10 to?
If you need time to 3 is fine.
Okay. I shouldn't do that. So this is once you've got these various algorithms that are producing features of the system. Features are things like what I just showed there. This algorithm output that you might threshold. That tells you maybe that something is going wrong. We also want to be able to act on that information. One way to do that, or an effective way to do that, is to fuse all that information through either a rule-based system or something more sophisticated to give us a diagnosis that says this is wrong with your engine, take this action. And this is an expert system, so a kind of a rule-based system that says if that that, and that happen, then you've probably got this type of fault. So we've developed this knowledge base that collects all that information and outputs an isolation of the fault, tells you what the fault is. And the way that works is like this. Takes in the features, from all over the engine, all the possible things you can think of, and it maps those with various weightings to particular failure cases. So this is saying if this feature here, which is feature 1, feature 2 and feature 3 are present, that means that we've got some confidence in failure type 2 occurring. And if failure type 2 has occurred, we can then say that means that either this particular component is at fault or this particular component. So we've got this system, and it allows us to do diagnosis. I think the really clever thing that we're doing now is looking at, okay, how can we close the loop on that back to control? Once we've said this particular, I don't know, let's say a generator's stopped working very well on an aircraft, how can we compensate for that in some way with a control system? We've got 2 engines on our aeroplane. Why don't we reduce the load on this generator if it's not working very well and it's about to fail? Why can't we take more load off the other generator that's sitting on the other wing to compensate for that? So so things like this, put into a closed loop, allow us to think about the control modifications we can make to the system. So point there is diagnosis isn't just saying something's happened, it's saying what do you do about it. Okay. So I think it's just to summarise really what we've some of the things we've been doing at the UTC. We start off at the top. Ever so important, the system design analysis. If you develop a wonderful algorithm that can detect something that no one cares about, it will never get implemented in the real world. So it's the message we always get told us from our industrial sponsors is make sure that you can prove the value of what you're trying to do. We use that value statement, as it were, to work out what faults we want to be able to detect. Very difficult to do that because data isn't readily available. No one wants to break things for the sake of it. So often you have to build your own, you have to find your own sources of data, you have to build your own rigs to be able to generate this data, to be able to then inject faults and train your algorithms. And there are numerous algorithms that you can use, as you've been talking about this week, that can be exploited to pick out the early signs of failure. Once you've done that, you've got some features, you need to do something about that, so you need to act on that information, and you probably need either some sort, or one way of doing that is through, one automatic way of doing that is through an expert system to interpret the output of your fault diagnostics. So, business case at the top, your sensing aspect to get the right sort of data, your analysis and the transfer of that information, and then acting upon it as a constituent to a successful EHM system from what we found with working with our partners at Rolls-Royce. So, happy to take any questions, if there are any.
Thank you very much, Andy. Thank you. Questions?
I can just do a bit of a sales pitch for our projects, actually, if that's all right, while you're getting that. Just to say, I guess you're all doing projects in the summer. Please keep your eyes out for projects associated with Rolls-Royce. There will be some health monitoring projects if people are interested in that, of various sorts, not just on what I've talked about today. So we're very welcome you to apply to those projects really, and see whether you find them interesting, I hope.
I thought you were a very interactive class. Do you have any questions?
Kind of, since we have a database, right, and the whole modeling is like